Great. I will present a very new guide among other EURAMET guides. It's dedicated to the calibration of automatic catchweighers. Probably you could be familiar with the EURAMET guide for non-automatic weighing instruments, but it was a challenge and a need from the European industry to develop a guide to cover the field of automatic weighing instruments, especially the automatic catchweighers. For the beginning, a short presentation of this kind of instruments. So basically, these instruments are used to weigh pre-assembled discrete loads, especially pre-packages, but also for loads of loose material. The instruments could be basically divided into two subgroups. The first one is used for dividing pre-packages into subgroups according to their mass. Especially this kind of instruments are used in the production of pre-packages where loads which are not in agreement with the nominal mass, they are then divided into other groups. And another subgroup, it is called labelers or weight pride labelers. They are used to label individual packages of discrete load with a weight, or it could be possible with unit price or price to pay. So it is very important to provide suitable quality of measurements on these instruments, and there is strong need to provide traceability. The number of this instrument nowadays in the industry is very high, and it is very important that these instruments are not only used for legal metrology purposes. In legal metrology, we know that instruments require type approvals, require verification, but there is a large group which is not subject to legal metrology, and it is essential also to provide in this field proper traceability. The internal quality control is increasingly implemented in this field, and it's necessary to point out that there's important difference between the static operation of instruments, which is typical for non-automatic weighing instruments, and the dynamic measurement mode of operation, which is typical for automatic catchweighers. And especially for this kind of mode, for the automatic mode, for the dynamic mode, the traceability must be provided. The question was how to approach the calibration of automatic catchweighing instrument. At least in Europe, we noted two different approaches. The instrument was calibrated according to legal metrology OML guide or recommendation number 51. But the problem with this approach is that this guide doesn't take into account any uncertainty evaluation. On the other side, there is a EURAMET guide dedicated for calibration of non-automatic weighing instruments, but the instruments are calibrated in static mode of operation. But we'll see that there is an important difference between static and dynamic mode of operation. In the Europe, there was no harmonized guide which would be used among EURAMET members, but we, at least in Spain, the Spain accreditation developed guide which was used locally for exactly the same purpose. So the EURAMET guide, as it was pointed out in the introduction, was developed by a consortium of several EURAMET members and also a representative of industry were included in this consortium. And the guide is available from the last year on the EURAMET webpage, the part which is dedicated for the EURAMET guides. Basically, the structure of the guide basically followed the procedure of the calibration. First of all, there is it's dedicated to the selection of calibration points, selection of test loads. The next step is determination of the reference value of mass of these test loads. As the next step, it's necessary to apply the test loads according to procedures defined in the guide. Different measurements are carried out, and based on these measurements, it is possible and necessary to evaluate the measurements, to determine the error of measurement, and to evaluate the corresponding uncertainty of measurement. And the results are reported in the calibration certificate at the end. So the guide also provides some instruction which information are necessary to be included in the calibration certificate. It's in contrast to the non-automatic weighing instrument. Here, with catchweighers, it is not possible to calibrate a weighing range of the instrument because of the dynamic behavior of the process. So the instrument is calibrated in the individual calibration point, which are defined by selected test loads, and the result of calibration can be valid only to these selected calibration points. The calibration points are not defined in the guide quantitatively. In a way, the beginning, the middle, the end of the weighing range, but the calibration points needs to be agreed with the client. It can happen there is only one calibration point which is necessary for certain instrument, and it is the most important that actually the calibration points are defined by the products which are normally weighed on the calibrated instrument. It is not good practice to use the standard weights to calibrate such kind of instrument, because it usually happens that with the same nominal mass you can get significantly different response of the instrument, which is then related to the shape of the product, length of the product, orientation of the product on the transport system, and so on. But the most important is the test loads and calibration points are defined by the product which are normally weighed on the instrument. The calibration process itself can be very well explained through the error model which is used in the guide to evaluate the error of the instrument and to evaluate then the uncertainty of the measurement. Basically, the error model is simple. On one side, we have a test load where their reference mass needs to be defined. On the other side, we have response of the instrument represented by the mean indication. And the difference between those two is the error of the instrument in the dynamic mode of operation. First of all, I would like to say something about the reference mass value of the test load. Of course, this mass must be traceable, and it can be defined on separate instrument, which is usually non-automatic weighing instrument, or by integral instrument. This is the automatic instrument which is calibrated, but it must be used in the static mode of operation. The guide doesn't define the accuracy of such kind of measurements and accuracy of a control instrument, but the calibration laboratory must be aware of the expectation of the client and possibility of the calibrated instrument. So basically the accuracy depends on expected uncertainty of calibration. The reference mass value of the test loads, which are, as I said earlier, the products which will be used to calibrate the instrument. The guide basically described two methods to define the reference mass value. In both methods, the control instrument is necessary, but if the higher accuracy is necessary, the test loads are compared on the control instrument with the standard weights. With the second method, the test loads are only weighed on the calibrated control instrument. In both cases, the result is the reference mass value of the test load with certain uncertainty. It is necessary to point out that there could be a special issue with the air buoyancy correction, because the products which are measured on the automatic weighing instruments, their density can differ very significantly from density of standard weights. But on the other side, this density of product, the same product are used both for calibration and both in operation of the instrument. So in a way, the density of test load is of little relevance. I will continue with the model for indication of the instrument, which consists of several contributions. The mean indication is the result of the several measurements of the test load on the instrument, and there are some additional contributions which needs to be taken into account. The first one is related to the resolution of the indication, the second one to repeatability, third one to reproducibility of measurement, and the last one to the effect of eccentric loading. In the guide, all these contributions, the expected value of all these contributions equals to 0. But of course, their uncertainty need to be taken into account. So now I will introduce contributions related to the repeatability, reproducibility, and effect of eccentric loading, and measurements which are necessary to be carried out for these three groups. Measurements which are necessary to evaluate the error of measurement and repeatability of the instrument, they are performed in all calibration points, and the number of repetitions depends on the mass of the test load. For larger masses, it is expected to carry out a smaller number of measurements. For smaller masses, the number of measurements could be higher. Based on these measurements, the mean indication is defined, and the standard deviation, which is then used to calculate the repeatability of measurement. The next group of measurements are done to evaluate the reproducibility. This is, in a way, something new. It's not included, for example, in the guide for calibration of non-automatic weighing instruments, but based on validations which were done during the preparation of the guide, it turned out that beside the repeatability effect, at least with high resolution instruments, there is another effect which needs to be taken into account, and these effects are taken on board with measurements made for the evaluation of reproducibility of the instrument. Basically, several cycles of measurements are done with the same load, and the operation of the checkweigher is interrupted between the measurements, and the load transport system is stopped between the measurements. And then the instrument is started again, and the new cycle of measurement is performed. Again, these measurements are performed in all calibration points. For each calibration point, based on the maximum difference of indication between the cycles of measurements, the reproducibility could be evaluated. The third group of measurements are done in order to evaluate the effect of eccentric loading. Again, these measurements are performed in all calibration points, but are necessary only if there are no guides to center the articles. If there are no guides to center the articles, one set of the measurements is done, first of all, in the middle of the load transportation system, then on the, let's say, right hand side, and then on the left hand side. And the largest difference between the middle and the left or right hand side is taken into account for evaluation of the effect of eccentricity. So with all these effects, it's possible to evaluate the uncertainty of measurement. But before coming to the conclusion, I would like to present a slide which is about the evaluation of consistency of measurements when the contribution of uncertainty derived from reproducibility measurements are taken or not taken into account. The measurements were done on high resolution instrument. For example, the resolution was lower than 1 gram. It was 0.1 gram, but the capacity of instrument was about 1 kilogram and more. And not taking into account, we got this result our error of measurements for certain number of cycles for the same load. The uncertainty is relatively low, but it can be seen that particular measurements are not in good agreement with another measurements of the same load. After the introduction of the reproducibility effect for the same measurements, it can be seen that more or less all measurements which were done with the same test load, not only single measurements, but each result represent a series of measurements as required by the guide. Then finally, these measurements were in agreement and a good consistency. It is necessary to point out that this effect can be very relevant for high-speed, low-resolution instrument. But on the other side, if the resolution of the instrument is not so high, if the instrument is not high speed, then the influence of reproducibility could be much less significant. But during the preparation guide, it was not possible to provide a clear instruction when these measurements to evaluate reproducibility are necessary and when not. So after the performing measurement, the final result are calculated, the uncertainty is calculated and reported in the calibration certificate. Of course, the calibration certificate need to follow the ISO 17125 requirements, but there are special special parts which needs to be taken into account for the calibration certificate for the automatic catchweighers. Of course, the general information about the instrument, the specific information about the calibration procedure need to be included, especially the description of the test loads, their orientation on the load transportation system, how their reference mass value was determined, what was the speed setting of the load transport system, and also the details of the loading procedure are relevant. Because any changing of these parameters can change the response of instrument, and of course the error of the instrument and uncertainty which are reported in the certificate. Further, it is defined which results needs to be reported in the certificate. Of course, information about repeatability, reproducibility, the effect of eccentric loading, the reference mass value, and finally the mean value of indication with the error of measurement and the uncertainty of calibration. Already during the presentation, I mentioned that there are some but important limitations to the method. It is important that calibration conditions are as far as possible close to that of the actual weighing process. Any change of the calibration procedure can bring different response of the instrument and can invalidate the results which are reported in the certificate. So the validity of calibration result is limited to the measurement points, which are defined by selected test loads, which are further defined by the products which were used for carrying out the calibration. It is important how the loads were positioned and orientated during the calibration, and what were the setting of the load transportation system during the calibration. As I said earlier, the calibration is not valid for a complete weighing range, but only for the calibration points. If the user of the instrument will introduce new products on the production line, the calibration needs to be repeated because the previous calibration were valid for the earlier test loads, earlier products on the system. The minor comment, the method is not intended for the calibration of vehicle incorporated or vehicle mounted catch weighing instrument. So with that I come to the conclusions. We believe that the EURAMET guide provides feasible and suitable information which will ensure harmonized and traceable dynamic measurement of on automatic catch weighing instrument. This will help to monitor, control, and improve weighing process in all industries which are where these instruments are used. It is important to point out that uncertainty depends significantly on the properties of the calibrated instrument, and the calibrating laboratory cannot influence this uncertainty a lot. And it's a good point that the EURAMET calibration guide is providing harmonized guidance, which could be further used by accreditation authorities and by calibration laboratories, and by this the formal traceability of measurements in this for this instrument which will be provided. So with this I finalize the presentation. Thank you for your attention, and I'm open for your comments. Thank you very much.